true. If the voltage across this capacitor is equal to the voltage across the battery, then there's no current flowing through the capacitor.
Now, in the series circuit now, does one capacitor charge at once, or I mean, like, no, I guess that is. So as the capacitor's first capacitor is still being charged, the charge that gets through is building on the second capacitor.
Yeah, you know that this is plus Q, minus Q, plus Q, minus Q.
But you won't have a case where the first capacitor charges up completely and the second capacitor gets nothing.
Impossible. Because where would if this was charged up, where would the charge from this plate have gone? It would have had to go in the second capacitor.
Right.
Now it might be that by hooking up multiple capacitors, there's the total charge that gets charged up is greater than or less than what you would have with another combination of capacitors. But they will both stop. They will both stop charging at the same time because the current in both of them has to be zero at the same time.
So there's one lecture on complex numbers. Is there anything?
The biggest mistake of my career. No, it wasn't. I mean, maybe it was. But there's nothing on complex numbers. Absolutely nothing.
Sorry, I'm just thinking about the complex copy.
You know, when I know you're probably all wanting to get back to study, but if you'll indulge me in a little story, very brief. When I was a grad student, I was a TA for professors in grad school. And we actually, where I was in grad school, we had to go to the classes of the professors that we TA'd. So then when we helped the student could say, remember when he did this in class? And we'd say, oh yeah, I was there. Okay, so I would sit in class, and I would watch the professor, and I'd think to myself, God, this guy stinks. If I ever teach physics classes, I'm never going to do this, pretty much everything he does. And one of the things that I said I was never going to try to do was believe that I could teach students math in the physics class and then expect them to turn around and use it like that. And lo and behold, I've become what I hated, because that's what I did. That's what I did with the complex numbers. So, as a result, that will not be in the museum, and you'll never hear about it again.
Do you do an example problem that has to do with like Kirchhoff's rules? I was just confused like as it's like the rules were.
Okay. You want me to solve this?
Yeah, I wasn't sure like I was confused like how you you want me to diaries man?
What is 18 volts, 12 volts?
That's a good one.
2 ohms and 1 ohm. So the first rule, if you're using Kirchhoff's laws, although they won't be on the exam in this form, is to label the currents. Okay, so the minimum number of currents we need to describe this, there's this branch on top, there's this branch on bottom, but since current can flow across the middle too, we don't know that these two have to be the same. So I can call this I1, call this I2, and therefore I could call this I3 in this direction, but now if I apply the junction rule, I know that the current out of this junction has to equal the current into this junction, so this one has to be I1 plus I2. That's not the answer to the problem, that's just the first part of the setup.
Well, wouldn't that be the answer? Just like did a current divided by that? Because it defines that current with the resistor. So just have to, if you, I mean, okay, that is. Wouldn't you just do you would find the current through the top two branches, or the top and bottom branch, and then just add that to get the middle branch?
Yep. But you do have to use the loop rule to solve that. But
yeah.
Okay.
Will there be an LC circuit?
Yeah.
Right, I mean, will there be like transients that go to like switch like vice versa, or vice versa?
If there are transients, you will not have to calculate the details of. You won't have to use the sines and cosines. Oh no, a transient would be for an RLC circuit. Where okay, circuit would just oscillate,
Yeah.
that might be on there, but it doesn't have a transient because it does the same thing for all time. Oh, I meant to say this to everyone, but it didn't happen. I am sorry about the thing with oak and the displaying the wrong grade. That's really, I mean, I want to say, I don't want to pass the buck, but it's totally not my fault. That was a bug where Oak was showing me that the grades in the class were the average grades in the class were one thing, and a student just happened to email me and say that, tell me, well, the average in the class is this, and I said, no, that's not the average in the class. And then I logged in as like a dummy student account that I have, and so like I look like a student, and it showed that it wasn't showing. It was showing totally different numbers. So I took screenshots of it and I sent it to the Oak people, but I don't know when they're going to fix it. I think that problem is fixed now, and so that's why I sent you guys the numbers in the real email. However, that doesn't change. I mean, there's no problem with how the grades are being calculated. There was just old data being shown in Oak. So, nevertheless, I realized that it was disappointing to find out that the class average was quite a bit higher than it was showing. But there'll be a curve. There'll be a curve.
As far as Andrew's log is.
Unless like everyone gets an A on the final or something. Okay.
Okay, as far as Andrew's log is it going to be more like conceptual or probable?
Conceptual.
So to clarify once and for all, hollow sphere with potential V outside has potential V inside, but a conducting sphere like solid sphere would be zero because
If it's a solid sphere and it's a conductor, then it's the same as a hollow sphere because all the charge will be on the outside. If it's a solid sphere and it's an insulator, then the charge, wherever you put the charge on the sphere, will stick to that point. And so the potential inside could vary depending on where you put that charge on the sphere.
if it's a solid conducting sphere, doesn't that mean that I guess that means there can't be an electric field inside.
That's right.
But there can still be a potential on the outside.
Yeah, because wherever the electric field is zero, you know the potential isn't changing, but you don't know that it's zero. So if it's V on the surface, and then the electric field inside the surface is zero, you know that the potential can't change inside. So it must be equal to whatever it was on the surface.
So the reason the charge in the inside of the conductor is zero is because all of it moves to the outside.
If it was a hollow sphere, does that mean that the potential changes as you get closer, like even inside the sphere, does the potential change at all?
It changes as you get closer
To the sphere from the outside.
from the outside. Okay, it depends on what the sign of the charge is. But let's say it's positive charge sphere. Then you imagine you're bringing a positive charge in. You're having to do work on that charge. It's like pushing a charge uphill. It doesn't want to get close to that positively charged sphere. So there's a potential. All right, it's zero out of infinity, and it's some value when you get right to the surface, and we'll just call that V. Okay. Then let's say you make it inside. Okay. Now there's no electric field. So you can move that charge around inside without doing any work at all. So you're not changing the potential energy of the charge. So you're not changing its potential. So it goes from zero to some fixed potential on the surface of the sphere, and then it stays at that potential inside the sphere.
And you know that there's no electric field that's inside the sphere because it's a conducting sphere?
Yeah. There's a picture, there are little pictures in your book about why that has to be true. And it's great to understand why that has to be true, but at this point it's 99% important that you just know that it is true.
Well, I mean, it's because like the length so it's exactly perpendicular to the charges aren't moving.
That's part of it. That's why the electric field has to be perpendicular to the surface.
For the Coulomb's law of multiple charged particles, don't we have to calculate the work we need to bring charged particles inside the magnetron?
Possibly.